So, even more BGP. This afternoon we are going to have a look at our full mesh issue that we have with iBGP inside an autonomous system and some stuff we can do to make that less painful. So, the problem, as we talked about earlier, we have this loop prevention rule that says an iBGP peer is not allowed to advertise a route it got from an iBGP peer to another iBGP peer. So router 2 gets a route from router 1, it can't pass it to 3 or 4. Same with all of them. So what does this mean? In effect, in order for router 1 to tell its neighbors about this route it has to have a direct peering relationship, a neighbor statement to each of the other 3 routers. And they all have to do the same thing. So we have a full mesh. So if some of you did CCNA or something way back in the past, you'll have seen that formula before if you did frame relay or wide area networking or something like that. So you can use that to plug in a number of routers and figure out how many peerings you would need. And it gets quite high quite fast. So, but we need a loop prevention mechanism. So the full mesh rule is there. Pretty quickly, as the internet started to get kind of big in relation to what they started out thinking it was going to be, they realized this wasn't going to work. So independently, 2 solutions kind of emerged. One was to use route reflectors, and the other one was Confederation, which is where you split an autonomous system up into smaller autonomous systems that are hidden from the world outside. Is one of these approaches better than the other, or recommended or preferred? Not really. It's a matter of these things both came out at a similar time. Some ASs use one, some ASs use the other, and they're not going to change their whole infrastructure just to suit somebody's design preferences. If it's in and it works, they'll build on that. So that means effectively you have to learn about both of them, because which one you might get exposed to depends on where you end up working. It's also possible to mix and match them, helpfully. So you can have route reflectors inside confederations and stuff like that. Just blows your mind. So, but all of these things are ways to try and get around this peering rules. So what can we do? Well, the first thing is, if we have to have the full mesh, and there's some reason we have to live with it, maybe in the question you get, they just tell you, don't use route reflection or confederation, then, but minimize the amount of configuration you have to do, then that might lead you towards something like this. So with a full mesh, there are advantages. You get resiliency, there's peering to everybody. You're not so worried about your next top resolution issues because you've got connection. Well, at least you've got peerings to all these other routers. But if you've got a big network, so that's that formula again, 500 routers gives you 124,750 neighbor statements to type, which is kind of a lot. So that means on router 1, you have to manually type the neighbor statement, update source loopback 0, and then whatever else comes after that. There might be a whole set of stuff. Maybe you're changing next hop addresses. Could be a load of things under the neighbor statement. And you have to do that on all of them. So 10 neighbors, you have to do this 10 times or 9 times on router 1. Then you have to do it 9 times on router 2, 9 times on router 3, 9 times on router 4. Gets out of control pretty quickly. Yeah. So what can we do about this? Well, if we have to stick with our full mesh, then we can do this. So we can use what's called peer groups. And this is just a way of optimizing your configuration. It doesn't really do anything else. Technically, it's no different than if you typed all the commands like we had here. Right? Technically speaking, the output at the end is the same as that. But if you have the same configuration going to multiple peers, then you can save a bit of typing if you do this. So when you configure your neighbors, you create a peer group called iBGP. So this is just a name, yeah? Colin, if you want. And then you put in the commands that all of you, the neighbors, are going to have in common. So if everyone's in AS100, you can say under your peer group statement, neighbor, peer group name, remote AS100. Neighbor, peer group name, update source loopback 0. And then when you type your neighbor commands to the actual peers, you say neighbor, whatever the peer address is, and then you say peer group, the peer group name. So that means 150.1.1.1 will be in AS100 and will use update source loopback 0. So will 2, so will 3, so will 4, so will 5. As far as that slide goes, it doesn't actually look like that big a deal, not much of a saving. But if you've got half a dozen commands and that you're going to have in common with all of these, for all of these neighbors, all of these peers, and you've got a lot of peers, you can see the value of it. It's a lot less typing, it's also a lot less mistakes, and it's easier to change because this would get applied to everybody. Yeah. It doesn't stop you then saying neighbor 150.1.1 and then something specific you need to do just on that neighbor, that peering. Okay. But it's a way of minimizing the amount of typing you have to keep up with. Okay. But only for commands that all of the routers you want to use this on have in common. Otherwise, you'll end up configuring stuff you don't want on certain peerings. But we get the idea of that? Just an efficiency thing. It saves us doing quite so much typing. But once we get over, you know, a few dozen routers, we probably don't want to even be doing that. It's too much extra work to control. It's also too much to go wrong. There's too many chances to make mistakes. And we've seen what can happen when you make mistakes in BGP. So, not a good idea. But small scale, that's something we can do. But if we want to not have our full mesh requirement, then there are ways we can get around it. There are solutions there. So the first is called route reflection. And this works inside of an autonomous system, not between them. So the concept is quite similar to what we saw with the designated router idea in OSPF. You've got somebody collecting routes and passing them on to other peers, like a designated router would do for a segment. So in this scenario here, if we don't want all of these routers peering with all these other routers, what could we do? We could say that one of these routers is a route reflector. So let's say router 2 looks nice and central here, so we'll call that a route reflector. And what that's going to do is take routes from other routers and pass them on. Breaking the rule that we just talked about. So instead of everybody peering with everyone else, oh, could have left that one. Now, sorry, I just realized I want to keep that. Okay, instead of everyone doing an IBGP peering with everyone else, which I'm going to represent with a red pen here, okay? Now we'll have the root reflector peers with the other routers. So we have an IBGP peering between 1 and 2. We have another one between the root reflector, which is 2, and router 3. And we have another one between 2 and 4. So these BGP speaking routers are connected to a root reflector. And weirdly, the way that you do this is to configure that on the root reflector. So you say router 1 is a root reflector client, router 4 is a root reflector client, router 3 is a root reflector client. You don't need to do it on these ones. You just do it there on the actual root reflector, and they all learn this. So now instead of having a full mesh, we have a hub and spoke. Yep. So the hub is the root reflector. So the root reflector collects roots from its IBGP peers and passes them on again. So this is the idea. Everybody gets the roots, but we don't have to have so many peerings. So that's cool. But there are issues involved in this. If you have a full mesh, these routers can all be choosing their best path to a particular destination, which might suit what you're trying to do. I mean, I've got 4 routers that look like they're close together, but we could have a global scale network going on here, you know? They might have quite different requirements on router 3 and router 1 because they're in different parts of the world. Yeah. If we use root reflection, then what everybody gets is the root reflector's view of the world, what the root reflector wants to do. So you might end up with less choice in where things goes. Another issue is that the root reflector doesn't modify root attributes like the next hop when it reflects the root. So again, you might have a topology that doesn't actually reflect where you would want things to go when you actually look into this. And you can use that to your advantage. What do I mean by that? Remember, there's another thing going on here. There's the IGP. So say you're trying to get traffic between AS2 and AS3. So routes come in, they get passed to router 3. They get sent up to the root reflector. They get sent out of router 1 over into AS3, etc. The actual path that the data might take is going to be trying to get from router 3 to router 1, presumably. And the path that OSPF or EIGRP or RIP might have for that inside your network might not involve router 2 at all. So maybe in order to get to 1.1.1.1, if this was the next hop for the routes towards AS3 or through AS3 to somewhere else, if that was the case, then your IGP is trying to resolve that address on router 1. So the actual path that traffic might take is down to OSPF, and maybe it wants to go that way. So router 3, if the route came from over there, router 3 gets a route from its IBGP peer, which is the route reflector, but that route has a next hop in it of that one. And OSPF says to get to that one, go that way. It's all fine. It's good, in fact. This is what you want normally. Because, remember, this is BGP we're talking about. So if this is a BGP router and you haven't stepped back the routing table, say that has full BGP routes or something, then this is trying to deal with 760,000 prefixes and possibly millions of routes to those prefixes. You don't really want it trying to move packets at the same time. It's got enough to do just forwarding routes around, keeping that going. So we can use route reflection to separate the control plane of the network from the data plane where the actual packets go. So the routes get sent up to the central point, the route reflector. The route reflector tells all our IBGP routers around the world where to go, where the next hop is, and then we leave it to OSPF to get the traffic to those next hops. And that may have nothing to do with this route reflector at all. And it's usually better if it doesn't, because you don't want that one doing two jobs. You don't want any traffic going through that because it's already getting hammered just coping with the routing table, let alone anything else. Yeah, so we separate the two things out. Data path is following OSPF, but the actual to the BGP next hop, but the actual routes are being forwarded or distributed across a different path. Okay. Now, when we talk about route reflection, I'm going to go back to that in a minute or two. When we talk about route reflection, when you read up on it, it's usually explained in a way that I find confusing. So they have these three rules. But if you actually look at the three rules a bit more closely, all you really need to remember is the last one. Because what does this say? Routes that we learn from an eBGP peer, so say we had an eBGP peer to a route reflector. Routes that we learn from an eBGP peer can be passed by a route reflector onto other eBGP peers if it has them, or a client, or another box called a non-client. So what that says is eBGP routes can be passed to everybody. Client-learned routes can be passed on to eBGP peers outside, can be passed on to other clients, and non-clients. So say 4 is a non-client. Okay. There's a peering, but it's not a route reflector client. We haven't said this is a route reflector client. This one is, that one isn't. So client-learned routes can be passed on to external peers, other clients, and non-clients. Everybody again. Routes that you got from a non-client can be passed to external and clients. So there's only one rule that matters from the point of view of working out what a route reflector will do, which isn't actually stated there, but you should be able to tell what it is. Somebody tell me what it is. What you was the question? What could you condense all of that down to in one sentence? No. A non-client route cannot be passed to another non-client route. Anything else goes. Yeah? So you can try and remember every bit of all those three rules, or you can just remember non-client can't be bounced to another non-client. It's the same thing, but it's a lot easier to keep in your head. Yeah? Because every other permutation is allowed in those ones. Okay. So we reduce our p-rings because we don't have to have IBGP p-rings between these other ones. We have this hub-spoke idea. Yeah. So this idea of a root reflector with its clients, that's called a root reflector cluster. And this is going back a slide. And each cluster has a cluster ID. So the idea is we've now broken our full mesh rule, right? So we don't want routes which started out in our cluster looping back round into our cluster again, because we would have made a loop, which we used to break with the full mesh. Yeah? But now we don't have a full mesh. We've got this hub spoke. But we don't want something managing to get round back in again. So our root reflector cluster has a cluster ID, which says effectively, if you see this ID, dump it because it came round through us before. Yeah. Okay. Similarly, same sort of idea. Generally, with IBGP, routes have the originator ID, the router that originated the route. And if you see that, your own originator ID, you would dump that as well on a router level. But on a cluster level, root reflector cluster, you see the cluster ID come back in, you reject it. Okay. So we need to add this in because when we got rid of the full mesh, we now have that potential for loops again. Yeah. Okay. So we have these different types of p-rings now, eBGP, IBGP clients, IBGP non-clients, and these complicated rules, but those complicated rules just distill down to non-client route can't be passed to another non-client. Yeah. Believe me if you like, or don't believe me if you like, work it out. Yeah. Okay. So you can also have multiple root reflector clusters inside your autonomous system. So this might follow geography to some extent. You might have some in different parts of the world. So you can do this in a few ways. You can try and keep different root reflectors to different regions so that region B of the world isn't affected by a problem in region A. You can also have multiple root reflectors in the same cluster. So the idea being if one fails, you have another one. Root reflectors can be clients of each other as well. So you can scale it up in this way. And if we're doing multiple root reflectors in the same cluster, that cluster ID will allow us to get rid of routes that have already been around from the other root reflector as well. So as well as a loop prevention thing, it also is an efficiency thing. We're not going to keep sending these routes around that we've already dealt with. So there's a link here, BGP case studies, which takes you to various implementations of root reflection, and I'd recommend having a look at it because there's various cases for this. And especially when you look at all this stuff, they tend to explain it in terms of these three rules. And if you're anything like me, you're trying to parse the behavior with all these three rules, and it's doing your brain in, trying to work it out. But when you're reading them, just remember it all boils down to non-client can't pass a route to another non-client, or the root reflector can't pass a non-client route to another non-client. Anything else works. Those diagrams get a good bit more simple when you understand that. Yeah. At least that's what I think. Okay, so root reflection turns this full mesh into a hub spoke, essentially. And it also lets us separate the control plane, sending our IBGP routes to IBGP neighbors, from the data plane of traffic trying to get to the next hops of these routes. Okay. We also have this cluster ID working as a filter mechanism, a loop prevention mechanism if you have multiple root reflector clusters. So if you have root reflector clusters and they're configured as non-clients of each other, then this rule comes into play here, where if you have routes which came from root reflector cluster 1, get passed on to 3. 3 can't pass them on to 2 because it's a non-client, etc. So you would have to make them clients of each other if you wanted to do that. And hope you don't get a loop. So cluster ID is a loop prevention tool, really. Configuration of root reflection, it's not that big a deal, especially if you're using peer group configuration. So here, we're just saying on the router that we want to be the root reflector. You make a router a root reflector by configuring on the neighbor statements that it has root reflector clients. So you tell a router it has neighbors which are root reflector clients. That makes it a root reflector. And it makes them clients. You don't do anything on the clients. So to set up a root reflector cluster, all you need to do is that. Now you could do it on every neighbor, so you could say neighbor 150.111 root reflector client, 122 root reflector client, 151.33 root reflector client. This example here is using the peer group stuff we'd already done from earlier on. So we just say because all of these routers will be part of the same root reflector cluster, they'll all be root reflector clients. That's a line we could put into all of them. So we just say neighbor, the peer group name, like we had before, and that this is a root reflector client. So all the routers in this peer group will become clients of this root reflector. And to make something a non-client, you just don't say anything. Yeah. So it's a lot harder to understand than it is to type. It's one of these things, you know. Okay. But the whole point of it is to reduce peering. Okay. So that was one approach to reducing peerings. The other approach was something called BGP Confederation. So the concept behind that is that you take eBGP rules and you apply them inside of an autonomous system, which you're not supposed to be able to do. So what in effect happens is you have inside of an autonomous system you have this is called a Confederation ID. There's the AS number that the rest of the world knows about. Okay, the rest of the internet knows about, AS1 here. So when we do the configuration, this is called the Confederation ID. And that's what the outside world sees. The rest of the stuff is invisible to other autonomous systems. It only happens inside. Inside of AS1, you can have multiple sub-autonomous systems. So here's 3 sub-ASs. And we tend to use private AS numbers from the top of the scale, that we talked about in the morning. So let's have 65001, 65002, 65003. So these are the AS numbers of the sub-autonomous systems. Now, inside of these, full mesh rules apply, just like we had before. But between them, we've just got directly connected peers. Yeah. So if we've got, these are meant to be routers. Inside of each of these systems, sub-ASs, we need to have a full mesh. But between them, we just need to have eBGP peerings. So we reduce the number, the total number of peerings overall, because all of this is really inside one system. Yeah. So we're artificially fooling the routers into thinking that there's eBGP going on in here when there really isn't. Yeah. So then what you have is a confederated eBGP peering there, there, and there, and then iBGP peering inside of each one of these. So overall, you get a reduction. So in here, routers in AS65001 see these as what they call Confederation peer autonomous systems. These are Confederation peers. You have to tell the routers which ones are sub-autonomous systems and which ones aren't. And then from the outside world perspective, this is just AS1. And somebody over in AS2 will just have a peering to that router there, for example. And as far as they're concerned, their neighbor is in remote AS1. They don't know anything about all this 64, 61,000, 65,001 stuff. All they know is that it's in AS1, because it has the Confederation ID of AS1, which is the real AS number as far as the rest of the world sees. So they don't know anything about 65 blah 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 outside. So this is a long way for a shortcut, but it's another way we can reduce our full mesh. Yeah. So both of those things, confederation, route reflection, they're trying to use these tricks to cut down on our full mesh. They're both trying to do that. If you want to give yourself a real headache, you could configure root reflection in here. So you don't have to have that anymore, and that can be a root reflector. You can mix it up if you want. Okay. So at least at a concept level, we understand what's going on with this. Blank stares. Good thumbs up from the back there. Grudging, yeah. Okay. Does anyone want me to explain that bit again? Please don't explain that bit again. Okay, right. So we split our single AS up into a bunch of sub-ASs. Rules that we follow between them are eBGP, and we use private AS numbers so that we don't leak information out into the rest of the internet by accident. Real outside ASs don't see any of this. They just see the Confederation ID, which is the real AS. And it lets you do different things in different parts of your autonomous system. Nobody else knows anything about it, and it doesn't change your next hop from system to system. It still does that change it on the way out rule that we saw before. Now that we've included a new level of hierarchy, even though it's hidden, we need some way to figure out if we've been through this sub-confederation before. So we have a couple of new attributes. So you have AS confed sequence and AS confed set, which will tell you, have I been through this path of sub-autonomous systems before? Yeah. Okay. So configuration-wise, if you can make this out, we have the green here. So this one is related to your INE topology. Yeah. So the green one is saying that this is AS100. Yeah. So Confederation ID is 100. That's your real AS. And then we've got these routers 1, 4, and 6 up at the top of the diagram in your lab topology. So these routers all have the same AS number. So they all have the same sub-confederation AS number. So they're going to run iBGP peerings inside this sub-autonomous system, which is 65146. So the network statements are just saying what networks are involved. We'll get to that next week. But then if we look at the neighbor statements, routers on router 1, routers 4, and router 6 are in the same sub-AS as we are. Yeah. Router 1 and 4 are in the same sub-AS as router 6 is. Same over here. Then, if we look down here a bit, you'll see we've got a link over to router 3 on router 1 here, which is saying that we have a link to a remote AS of 65379, which is another sub-autonomous system. Yep. So that's another sub-ID, and we tell the router, which is so if I change this, So this is 146. This is router 1, router 4, router 6. Matches up with that, yeah? So these neighbor statements where it's the same AS number, remote AS 146, these are routers inside the same subautonomous system as we are. But then we also have, on the router that has connections outside of this sub-AS to other sub-ASs, we have to tell that one what other sub-ASs it can connect to, rather than real external autonomous systems. So we have to tell them these ones aren't really external ASs at all. So we'd say on a router which has peerings to something outside, which is router 1 in this case, that it has connections to routers in these other ones. So we say you have peerings to 65.508, and you have a peering or another Confederation sub-autonomous system of 65.379 over here. So these are essentially like external BGP peerings, but they're inside the area, inside the AS in reality. So now, on router 1, when we say neighbor router 5, 65.508, neighbor router 3, 65.379, those are read as external Confederation eBGP, yeah, Confederation eBGP peerings to other subautonomous systems. This one here, where it says remote AS54, 54 is not in this list of Confederation peers. So that's how the router knows that this is a real external autonomous system. And when it's talking to a real external autonomous system, it's going to be using its real AS number 100, which is the Confederation ID in this configuration. So the router over in AS54 sees the AS path will have AS100 in it, not AS65.146 or 379. That's all hidden. Yeah. So you only need to do this Confederation peer command on routers which have peerings outside of the sub-AS. 4 and 6 on this slide don't have connections outside of the sub-AS. They just have peerings to router 1, and router 1 talks to the other subautonomous systems. So it's the only one that needs this statement. The others don't. But everybody needs to know what their sub-AS is and what their real AS is. Yeah, no. Hands up, no. Hands up, yeah. Hands up, most of you, yeah. So what you're trying to do is apply external BGP rules inside your internal autonomous system. Yeah. So we break one set of routers, these 9 routers here, which would have to have a full mesh of peerings from one router to 8 others, each router to 8 others. We say we can break this up by saying, you guys are really in, or you guys are in the sub-AS, whatever we say, 65.379. and you guys are in a different one, you guys are in a different one. This only happens in here, and now you have to have a full mesh inside your autonomous system, but and you only need to have individual peerings between autonomous systems, just like we have on the bigger scale, but we hide all this from the outside world. So we're applying the same kind of thing we do at the larger scale inside the system. Okay. But because we're now using our AS numbers to do sub-autonomous systems, when we make a confederation, we need something to tell our routers what their actual autonomous system is, which is the confederation ID. So they all think inside of here, they're in the AS you've configured them on. But, and they apply the rules accordingly. So this router in AS 65146 is not in the same AS I am, so this is an eBGP peering. But it's a confederated eBGP peering. And only on connections to the outside world do we worry about what our real autonomous system number is. And they don't know any of this stuff. They just see it all as AS100. Okay. All right. It's probably enough. Okay. For one day. Thank you.